Hello, quick video on introducing complex numbers. Quite often we spend a lot of time trying to solve quadratic equations, haven't we? Quadratics. And here's probably the most simple one that we can have, isn't it? X squared equals 1, and that gives us two roots, doesn't it? Therefore, x is plus or minus 1. Yep. And we've also looked at the fact that sometimes there aren't real roots, and that we've used the determinant b squared minus 4ac to decide whether there are real roots. So in the cases above here, that's greater than 0, so we know we've got two real roots, and on the right hand equation here we know that equals 0, so we've got one repeated root. So we're going to use complex numbers where we've got negative determinants. We need a method of dealing with those for equations, and there's our most basic one, isn't it? X squared equals minus 1. And we're going to use complex numbers, he's called, to deal with this. Excuse me, voice is going. Okay, so let's look at this really basic equation. And if we just followed our normal route here of solving this, we would just root both sides of the equation, recognise that we got plus or minus here. And so we'd have this square root of minus 1. And what we do is suspend belief in this area of having these called imaginary numbers. And we say, well, let's have a number. We're going to call it I, a bit like we call pi, and e. And we're just going to say I equals the square root of minus 1. So therefore, if we just accept that on face value, we know that x equals, the answer to this question, x is plus or minus 1. Okay, so let's use that approach and solve this quadratic at the top by completing the square, yeah? So what do? The first thing we do is, because we've got x squared minus 2x, we know that we're going to complete our squares x minus 1 all squared, take off our minus 1 there with our plus 4. So we then rearrange, so we've got x minus 1 squared equals minus 4. Therefore, taking our next step as we normally would, x minus 1 is plus or minus the square root of what we had on the right hand side. Now, square root of minus 4 is 4 times minus 1, so if we take the 4 out the front, out of the root, we get a 2, don't we? So therefore x minus 1 equals plus or minus 2 lots of square root of minus 1, and we have a symbol for that, which is I, so therefore it's plus or minus 2i, and therefore our overall solution pair is x equals 1 plus or minus 2i, and we could write those out as two separate solutions, separate roots, 1 plus 2i or 1 minus 2i. Now if we just accept that, we have an answer. It is a valid answer mathematically. Now we want to look at how we're going to present this. And what we're going to do is think about the fact that we start off here with our real number line, yeah, minus 4 all the way up to plus 4. And that we can deal with our real numbers, yeah? That would deal with our plus 1 here, isn't it? We could just draw our plus 1 onto this line, we know where we are. But we've got to do something with the 2i. And what we do is we look at that by creating an imaginary number line, and we write that vertically at right angles to our real lines. We've got a real line and we've got an imaginary number line there. And therefore, if we want to position the number 1 plus 2i, we just go along 1 in the real direction and then up 2 in the imaginary direction. And there we mark our point. And we usually call these, because these are complex numbers, we usually use the term z, because quite often people will look at that as being x plus yi. Can you see why they're doing it? Because they're making it a bit like an xy graph, aren't they? Okay, and this is called an Argand diagram, yeah? So we're just going to mark all our points on that. We had a second solution to this, didn't we, which was 1 minus 2i. There it is. This is the second point here. And can you see that these are effectively a pair, aren't they? 1 plus or minus 2i. And we've seen these pairs before, haven't we, in surds, and we call them conjugate pairs. And in complex numbers, the conjugate the one with the other sign on the imaginary part is usually use the symbol Z star. That's the conjugate, yeah? So here we can mark our two solutions to our equation, our quadratic, x squared minus 2x plus 5 equals 0, and we get these 2 points and we plot them on the graph. Obviously, if we had cases where there were valid answers, real answers to a quadratic, the numbers would be on this, purely on the real dimension, our real number line, but we can get these answers that are out there on the imaginary side. Okay. Operations of these complex numbers, well, we created them by using normal operations. I multiply, divide, add, subtract, and they still operate in complex numbers. They just have some slightly weird effects. Yeah, so we're all happy that 2 times 3 equals 6, etc. Or 2i times 3 is 6i. Or if we had a bracket here, 1 plus our 2i, and we multiplied by that 3, we'd get 3 plus or minus 6i. So that's all fairly straightforward, but we get some strange effects when we multiply two complex numbers together. So let's have 1 plus 2i times, in brackets, times 2 plus 3i. And if we just go through and do all our factors, so I've done it here by multiplying through the 1 first and then the 2i second. So I end up with 2 plus 3i, that's the first bracket. Then I'm going to multiply the set of the bracket by 2i, so I get 4i plus 6i squared. But we know I squared, therefore, is going to be minus 1. That's the final part of this, isn't it? If e is going to be minus 1, yeah? If I is the square root, I is the square root of minus 1, then I squared is minus 1, yeah? So I can just replace that with the I squared with a minus 1. So now I've got two real parts here, like 2 minus 6, which gives us minus 4, and a 3i and another 4i gives us 7i. And if we were looking at the conjugate pair, the 1 minus 2i did the same process. We get 2 plus 6 gives us 8, and 3i minus 4i gives us just minus 1i. So that all works normally. Division, so if I took the first one there, 1 plus 2i, and divide it by 2 plus 3i, well, I'd do what I would do to rationalise the base, the denominator, as we would in a surd. So there's my 2 plus 3i, and in order to rationalise it like a surd, I'm going to multiply it by the conjugate, 2 plus 3i. And the result of that will be that these first two terms multiplied together will give us 4, and the second two multiplied together, 3i times minus 3i, gives us minus 9i squared, which gives us 9, doesn't it, because the I squared is minus 1. Yep, so that's going to give us our 13 as our denominator. And then we just multiply through the top as we saw earlier, and our answer becomes 8/13 is the real part, plus 1/13 is the I part. And we can do the same thing here with the conjugate pair and do the division in the same way, and we would end up with the same denominator but different numerator, and we end up with minus 4 over 13 minus 7 over 13i. So all our rules work, they just have very strange outcomes. They're not immediately obvious, are they, what those outcomes should be? So if we started off as we did earlier, there's our conjugate pair we started with there. If we multiplied it by just an ordinary number, we got, right here was multiplied by 3, we end up with 3 plus 6i there, don't we, for that one, and that one should be 3 minus 6i for this conjugate pair being multiplied by 3. If we now multiply these two numbers together, we end up with a point over here, minus 4 plus 7i, and if we multiplied that number, complex number, by this one, we ended up with a number over here, and we'll come back to why that is in a further video. And we could do some divisions as well. So we divided one by the other, we got these other 2 points coming in closer, which we would expect, wouldn't we, because they're smaller. So all sorts of fun there, but we can map all these points onto our Argand diagram. Okay, so let's summarize this lot very quickly. We use the symbol I equals the square root of -1, and therefore it's probably worth just saying there I squared equals -1, and that's what we're using throughout here. That allows us to solve quadratics with non-real roots, hence we've always talked about having real roots, because here we have two roots and they are imaginary. Yeah, they are complex numbers because they have a real part and an imaginary part, and we can draw those onto our Argand diagrams. And if we're having roots like this, they come in conjugate pairs, and we use a symbol Z star to do that. And what we're changing is the sign of the imaginary part here, yeah? Because if Z 1 plus 2i is a root to this equation, then 1 minus 2i must be a root as well. Hope that's of use.